Hello, and welcome everyone to this second podcast for day 5, covering chapter 3. In the first podcast, we talked about the first two properties of water that made water essential for life. In this podcast, we're going to pick up from that discussion and talk about the remaining two properties of water that are important for life. And then we're going to close with a discussion of the pH and what acids and bases are. All right, well, let's go ahead and get started. Next, I'd like to talk about this third property of water that helps sustain life on Earth. And that property is the observation that ice floats. So water in its solid form, ice, floats on top of water. Another way we could say this, perhaps a little more scientifically, is that ice, the solid form of water, is less dense than liquid form of water. This means that in the solid form, the ice will float on water. What I'd like to do here is draw a few water molecules. And remember, they're going to hydrogen bond with other water molecules. In the liquid form, these hydrogen bonds are not very stable, or I should say they're less stable. And because they're less stable, they will form, like you see them here, and then they will also break apart. Then they'll reform again, and others will break apart. And remember, when you're looking at a cup of water, there's more than just 4 molecules here, billions of molecules. And so this constant breaking and reforming of hydrogen bonds within the water molecules allows it to have this liquid form. The hydrogen bonds are less stable. So let's write that down here. Liquid water, the hydrogen bonds are less stable. Now, as the water temperature approaches 0 degrees Celsius, that is freezing, what happens is these water molecules, the hydrogen bonds within the water molecules, will become more stabilized. So I'm going to redraw these here, like so. I'm going to draw one molecule here first. And I want to make a point here, looking at just this one molecule. It can hydrogen bond with 4 other molecules. 2 at hydrogen, and then it can bond with 2 other water molecules at the oxygen. As the temperature approaches freezing, and at freezing, every water molecule will bind with 4 other water molecules, and they won't break, because at 0 degrees or lower, the hydrogen bonds are stabilized. So this is ice, solid form of water. They're held at this constant equal distance from each other. Because of this, water in its frozen form is less dense. So this is an interesting fact, but why is it important to help sustain life? Because this is a biology class, it's not a chemistry class. So why is this fundamental chemical property important in sustaining life on Earth? Let's go back to our favorite pond that we talked about, or it could be a big lake, doesn't matter so much. And it's all liquid out here, it's warm temperatures. Now what happens though is as the temperature falls, let's say it's January and the temperature is below freezing. So temperature now is less than 0 degrees Celsius. The water molecules at the surface here will become colder faster than the water molecules here because they're closer to the cold air. As that happens, the hydrogen bonds within the water molecules here stabilize, forming ice. Now, having this ice form on the top here protects the water below it from the cold air on top, which allows the water below here to stay warmer. And all the life that is in this water, lake or pond, all this life now can survive. If ice was more dense than water, what would happen is as this top layer froze, it would sink to the bottom. Then the next layer on the water would freeze, and it would sink to the bottom. Then the next layer would freeze, and then it would sink to the bottom. Next layer, and it would constantly happen like this until the whole lake or pond was frozen. Luckily, that's not the case. Luckily, ice is less dense than water, and being less dense than water, it floats, which allows all the life down here to survive because the water is warmer. So the property of ice being less dense than water is very beneficial to maintaining life in areas where water can freeze. Alright, I want to talk about this last property of water that helps sustain life, and that is that water is a great solvent for life. So what do I mean by that? Well, I'm going to have to define some terms here. But before I do that, I want to remind you that chemical reactions in cells are done in an aqueous solution. And what I mean by an aqueous solution is just a solution in water. For instance, if we were to look at a cell here, and we'll learn about the parts of the cell later, and you probably have heard about them before, but you have your nucleus, you have your mitochondria, you have peroxisomes, you have Golgi bodies, and all that good stuff happening in here. What you also have is this cytoplasm. Cytoplasm is the aqueous solution within the cell. And if we were to put that in a tube, say, like so, what we would have in here is all the water that is in here, plus all the chemicals and all the enzymes necessary to do different reactions. The reactions of respiration, the reactions of fermentation, the reactions of photosynthesis. All of those biochemical reactions that you'll learn later about are in here, and all of those chemicals are dissolved in the water. You can't see them. They're one with the water, so to speak. So I want to define three terms: solution, solvent, and solute. And I want to do it by walking through a short example. If you had a beaker here of water, and you had a sugar cube, like so, and you mixed them together, you would end up with a beaker of sugar water. But you wouldn't see the sugar anymore because it would be dissolved in this water. So in this example here, the sugar is the solute. The solute is the substance being dissolved. The water would be the solvent. The solvent is the agent doing the dissolving of a solution. It is the liquid portion of the solution. The solute you can think of as the solid part that is being dissolved. And when they all come together, this we call the solution. And we can think of the solution as a homogeneous mixture of two or more substances. And what homogeneous means is all of the substance are completely dissolved. It appears as a single solution. And since we used water in this substance, more appropriately we could call this an aqueous solution. Okay, I'm going to erase this, and I'm going to talk about a couple of different ways that waters at the chemical level dissolves solutes. Water dissolves solutes that are either ionic or polar. Okay, let's start with ionic bonds. So we're going to take water, and remember water is H2O, so there are two hydrogens and the one oxygen, held together by a covalent bond. And remember the hydrogens are partially positive and the oxygen is partially negative. And let's mix that with some sodium chloride. And remember sodium chloride looks like this, Na plus and Cl minus. And they're held together by an ionic bond. And remember, ionic bonds are not as strong as covalent bonds. So how does water dissolve sodium chloride? Water dissolves sodium chloride by essentially pulling the sodium and the chloride apart and sequestering them, keeping them away from each other. And it does so by taking advantage of these partially positive and partially negative charges. So the chloride ion, I'm going to draw the chloride ion here, it's going to be surrounded by multiple water molecules because of these positive charges. Now water will also surround the sodium, but it's going to be the oxygen that interacts with it. This way, keeping sodium and chloride away from each other so that they can no longer form this solid compound of sodium chloride. This is also why at some point you can put so much sodium chloride into a solution and it will no longer dissolve, because at some point there's not enough water molecules available to sequester, to pull apart all of the sodium chloride. Next, let's talk about polar molecules and how they dissolve in water. Essentially, it's the same way. So let's draw a protein. I'm just going to draw a protein like this. And if it's a polar molecule, it's going to have either partially or fully positive charges or negative charges on the outside of it, like so. And what water can do now is it can form bonds with these partially positive, partially negative charges. So you can have your water molecule here bonding with that positive charge, or this hydrogen bonding with this negative charge, all the way around it, to the point where the entire protein here is surrounded by water molecules, which allows this protein to be dissolved in the water. This is also how our sugar would dissolve in water, because sugar itself is not an ionic compound, it is a polar compound. And being polar, it interacts with water in a similar way to dissolve that sugar. Alright, now I want to introduce two more terms for you as they relate to water as a solvent. They are hydrophilic and hydrophobic. Hydrophilic, if you translate it, literally means water loving. Hydro for water, philic for loving. Now, it doesn't really love water molecules. All this really means is that that substance, whatever it is, interacts with water in much the same way we talked about the sodium chloride in the protein and the sugar. It can be saturated with the water molecule, which dissolves it. So in our last example, sodium chloride, that protein, and sugar are hydrophilic. Now, as a point of reference, not all proteins are hydrophilic. Some proteins are hydrophobic, which, if you translate it, means water fearing. Now, these substances aren't really afraid of water. It's just the way that they originally described it. But what this means is that these compounds cannot be saturated with water, so they don't interact with water. And so they can't dissolve in water. This is really important. Things like lipids are hydrophobic. If hydrophobic substances like lipids could dissolve in water, then our cells would no longer form, because our cells are surrounded by a lipid bilayer. So it's incredibly important that things like hydrophobic substances don't dissolve in water. Alright, the last thing I want to talk about for this day are the terms acids, bases, and pH scale. Your book gives a very nice definition of acids and bases. The acid is defined as a substance that increases the hydrogen ion concentration of the solution, and a base is a substance that decreases the hydrogen ion concentration of a solution. I'm not going to ask you to define that on a test, or that won't be part of a multiple choice question. I want you to understand how to apply the terms acid and bases in certain contexts. So this is really what I want you to know. I want you to know the pH scale first. You should know that the pH scale goes from 0 to 14. You should know right in the middle, pH 7 is what we call a neutral pH. It's neither acidic or basic. You should know everything lower than 7, so 0 to 6.9 is acidic. And then you should know everything above 7, so 7.1 to 14 is basic. I also want you to know that what a buffer is. It's important that our cells and chemical reactions that you might be doing outside of our bodies, but our cells are these buffers are very important for our cells. And essentially what a buffer does is minimizes changes in pH. It stabilizes, is another way you can think of it, stabilizes. If we need a particular part of our cells to be at a certain pH, maybe slightly acidic, slightly basic, that cell cannot tolerate large fluctuations in pHs. So buffers are important to maintain that concentration, that pH value in that part of the cell. I also want to talk about a short example of how greenhouse gases can change pHs and how that's important for life on Earth. And so let's draw the ocean here. And we know in this ocean we'll have various coral reefs forming. We also know there are various organisms that require a shell. And they form these shells in this coral reef because of calcification. To get calcification, the ocean in general has to have or be maintained by a proper pH value. As long as this pH is formed properly or is maintained properly, calcification can occur and coral reefs can form. The organisms that live on coral reefs can form. Other shelled organisms can survive and reproduce. However, what we have learned over the years is there's a problem with greenhouse gases. And we'll talk about greenhouse gases at various points throughout this semester, but you've probably heard of them. A big one is CO2. It's a greenhouse gas. And CO2 is released from largely through the burning of fossil fuels. And what happens is that this CO2 will be dissolved in the ocean. And what happens here is that CO2, we'll just write it like this, CO2 plus seawater gives us carbonic acid. Having more carbonic acid in the ocean will lower the pH. It'll make the ocean slightly more acidic. In fact, we know that the ocean has about a 0.1 decreased pH, the lowest it's ever been in thousands of years. It's predicted that it could be as low as 0.5 pH values by the end of this century. So why does that matter? Well, it matters because having it be more acidic causes less carbonate ion. So let me say that again. So as the pH drops, I'll write that over here, pH drops, and that equals less carbonate ions. Carbonate ions are what are important for calcification. Without calcification, the organisms that rely and build the coral reefs and the organisms that need a shell to survive, those organisms are going to decrease in population because of the lower carbonate ions. And again, lower carbonate ions because the pH dropped. The pH dropped because we have more carbonic acid in the ocean. We have more carbonic acid in the ocean because CO2 is dissolving at a higher concentration in the ocean and mixing with the seawater, causing this acid. That is all I have for this particular day, day 5 of the class. If you have any questions at all, please make sure you come see me and I'll be happy to help in any way I can. I'll see you in class. Bye.